Hello, everyone. Welcome back to the YouTube channel, An American Professor. We're going to continue the reinforcement learning basic series. And today I'm going to be discussing different kinds of policies that are used by reinforcement learning agents to maximize the expected cumulative reward, or similarly, minimize the expected cumulative cost. Introduction. Given a finite state space script X and a finite control space script U, the two main types of policies in reinforcement learning may easily be defined. The two main types of policies in RL are deterministic policies and stochastic policies. First, let's cover deterministic policies, and then I'll pivot and discuss stochastic policies. But all of the spaces I'll discuss today are particularly for discrete and finite state spaces, no mention of continuous state spaces or continuous controls. Both the state space and the control space we're considering today are finite in nature. In a deterministic policy, the same control is always output for the same input state. So when we're in some state under a deterministic policy, an agent will always output a determined control, one control per state. It's a mapping, a deterministic mapping from the finite set of states to a finite set of controls. In my notation, I like to use phi to denote a policy, which takes as input a state X in the state space and always outputs the same control U in the control space. In short, a deterministic policy can be written as follows. U is equal to phi of X. So phi takes in a state and outputs the control U that the agent will use to influence the next state. The goal of RL is to learn the optimal controls U star of X for all X in the state space so that the sum of all agent rewards is maximized. And stated differently, we want to find what is that optimal policy, and RL algorithms are created to do such a task. Stochastic policies. On the other hand, a stochastic policy is only a little bit more complicated. A stochastic policy says that for any given state, each control is selected with some possibly non-zero probability. In my notation for stochastic policies, we can write it as phi of U given X. So we condition, this bar means condition on state X and returns a probability for selecting that control U, where the stochastic policy is conditioning on the current state. This stochastic policy notation is shorthand for the longer probability expression, the probability that the random variable U equals little u given the random variable X equals little x. An additional rule is required for stochastic policies, as here our stochastic policy is actually a probability mass function, and so it must sum to 1. That is one of the conditions of probability mass functions or distributions in general. They must sum or integrate to 1, and they must be non-zero or non-negative. They can be 0 or positive, the values of the distribution or the density or the PMF, but they can never be negative, and they must sum to 1. These are the main differences between deterministic and stochastic policies as used by agents in reinforcement learning scenarios when using finite state and control spaces. Next, I encourage you to follow this link and sign up to become a Medium member so you have unlimited access to all of my stories and never miss a new one. See you in the next video.